So now we're ready to develop our shape from shading algorithm. First, we want to talk about the representation of surface orientation. We've already talked about this in the past, but we want to make a slight change here. So we have represented surface orientation in the past using this PQ representation, the surface gradient representation. And this is just to remind you what that means. Let's say you have a unit surface normal n, which happens to make an angle theta with respect to the z-axis. Remember, the z-axis corresponds to the viewing direction v of the camera. So how do we go from n to PQ? We discussed this in the lecture on photometric stereo. We place a plane at z equal to 1, which is parallel to the xy plane. We'll label that as P and Q, the two axes, and that's our PQ space. And so to figure out what the PQ value for this unit normal would be, we simply extend this normal so that it intersects the PQ plane. And wherever that intersection happens, that PQ value corresponds to the PQ representation of this unit surface normal. So all that's good. We have used this in the past. But it turns out that it has one undesirable attribute, which is that when theta approaches 90 degrees, you can see from this diagram, P and Q can increase in value rapidly, and at 90 degrees, one or the other ends up going to infinity. That's a bit of a problem. As theta starts increasing from let's say that you start off with theta equal to 0, and theta starts increasing, P and Q values start increasing in a very reasonable way. But as theta increases more and more and approaches the grazing angle, P and Q values spin out of control. They move very fast. So one of the undesirable attributes here is that you have this sort of non-linear resolution in PQ space. So we want to bound these values of P and Q in some way, or surface orientation, surface gradient. And the way we do that is by using what's called the stereographic projection, or the FG space. So this is how we compute the FG values corresponding to a unit surface normal. So here's your normal right here, same angle theta. And on your z equal to 1 plane, we now label these as F and G. And the way you go from N to FG is that you take a point at -1 on the z-axis, this point right here. And you're going to draw a line that goes from -1 on the z-axis through the tip of the unit normal, and wherever that line intersects your FG plane, that's the FG value corresponding to this unit normal n. So that's the mapping in this case. So you can look at the difference in the mapping. Here you extend the normal, here you go from -1 through the tip of the normal, and you get FG. And there's a very simple relationship between FG and PQ. What you do is you consider this triangle right here. So you see this triangle in 3D. You take this point right here, which is the origin of your FG plane. You take the FG value, and you take the point where z equal to -1. That's one triangle. And then you have another triangle, which is the tip of this normal right here. And then the projection of the normal onto the z-axis, which would be somewhere right here. And then you have the z equal to -1 point. These two are similar triangles. And using those two similar triangles, you can come up with a simple expression that relates FG to PQ. So the point that I want you to take away is that the unit normal n is equivalent to PQ, and that's equivalent to FG. Now let's take a look at the advantage of using the FG space. So here is your stereographic projection space, FG right here. And let's consider this unit normal right here, which is aligned with the y-axis. So that's 0, 1, 0. And the FG value corresponding to that is going to be 0, 2. And if you consider this unit normal here, which is aligned with the x-axis, the FG value corresponding to that is 2, 0, right here. In fact, you can convince yourself that all the FG values that correspond to the visible hemisphere, so you have the camera looking from the top and you have a visible hemisphere which is the set of normals that fall on the upper hemisphere, all of those surface normals are going to lie within a circle in FG space of radius equal to 2. So that's the advantage of using this. So all we are going to do now is represent our reflectance map using FG rather than PQ. We know that N is equivalent to PQ, which is equivalent to FG. And this is our setup here. We have our camera in the direction V, which is aligned with the Z-axis of your coordinate frame. You have your source direction right here. You're going to assume that the light source is really far away, which means that all points on the surface of interest to you are going to basically be seeing the same source direction. And here is your surface normal right here. So you have I equal to Rs, S is for a given source, that's your reflectance map, as a function of Fg. If you tell me what the surface normal is, then I can plug that into the reflectance map and I can tell you, as we've discussed earlier, what the brightness is that it would produce in the image.